This video presents a simple example of reinforcement learning of AI in C++. We plan to make a follow-up video demonstrating the same examples in CUDA next month. Billy will first explain to you what reinforcement learning is.
Machine learning is generally classified into three paradigms: supervised learning, unsupervised learning, and reinforcement learning. In the previous two videos, we explored supervised learning, in which the machine learns from a training set of labeled examples. For instance, as shown in this diagram, the model is trained to classify inputs as either apples or oranges based on labeled data. However, this kind of learning isn't suitable when the goal is to learn from interaction rather than from labeled data. That's where reinforcement learning, RL, comes in. Interestingly, RL is also considered a form of unsupervised learning. There are no explicit labels or targets provided. Instead, an agent learns through its own experiences, interacting with an environment to achieve a specific goal. The agent is rewarded when it takes actions that lead to good outcomes. It is penalized when it makes poor decisions. This is similar to how animals, or even babies, learn through trial and error. A learning agent aims to maximize its reward by taking the most appropriate actions, as illustrated in this diagram. These actions don't just influence the immediate reward, they can also impact future situations and the rewards that follow, shaping the entire course of learning. Because a reinforcement learning, RL, agent isn't guided by manually labeled input data, it must explore its environment, trying out different actions to discover which ones lead to rewards. Through these reward signals, the agent learns to favor actions that have yielded positive outcomes, in order to maximize its overall gain. However, effective learning requires more than just repeating past successes. The agent must also continue exploring new states and actions. By doing so, it gains valuable experience that can further improve its decision-making. RL algorithms are designed to balance two competing strategies. Exploitation, choosing actions that the agent already knows will yield high rewards, based on past experience. Exploration, selecting actions with uncertain outcomes, to gather more information about the environment. The agent cannot rely solely on exploitation, or it may miss out on better strategies. Nor can it explore aimlessly forever, as this would prevent it from making optimal use of what it has learned. In general, exploration helps the agent discover new opportunities and learn about the environment. It involves a higher level of uncertainty and risk. Exploitation focuses on making the best decisions based on current knowledge, with the goal of maximizing expected reward, typically with lower risk. A reinforcement learning system typically consists of four key components: a policy, a reward signal, a value function, and optionally, a model of the environment. A policy defines how the learning agent behaves at any given moment. More formally, it's a mapping from perceived states of the environment to actions, essentially telling the agent what to do in each situation. In psychology, this would be similar to a set of stimulus-response associations or behavioral rules. The reward signal defines the goal of the RL problem. At each time step, the environment provides the agent with a single numerical reward. The agent's primary objective is to maximize the total cumulative reward over time. This signal tells the agent what is good in the short term. While rewards indicate immediate desirability, the value function estimates the long-term benefit of being in a given state. In simple terms, the value of a state is the total amount of reward the agent can expect to accumulate in the future, starting from that state. This means a state might have a low immediate reward, but high value if it leads to rewarding future states. Or a high immediate reward, but low value if it leads to poor outcomes later on. The value function helps the agent look ahead, evaluating not just immediate rewards, but also how current decisions affect future possibilities. A model represents the agent's understanding of how the environment works. It captures the relationships between states, actions, rewards, and transitions. A model can be used for planning, allowing the agent to simulate future actions and predict their outcomes. In reinforcement learning, two widely used methods are temporal difference, TD, learning, and Q learning, where the Q stands for quality. Temporal difference learning focuses on the changes, or differences, the agent observes over time as it interacts with the environment. Its primary goal is to evaluate a given policy pi, by estimating the value function v pi, the expected return for each state under policy pi. As the agent experiences state transitions, TD methods incrementally update these value estimates based on the observed differences between predicted and actual rewards. This makes TD learning powerful for online, real-time learning without requiring a full model of the environment. Suppose T denotes the current time step, and T plus 1 denotes the next time step. So ST is the current state, and ST plus 1 is the next state. The update of the value function VST is given by VST plus alpha times or T plus 1 plus gamma VST plus 1 minus VST, where R is the reward, and alpha and gamma are some empirical constants, referred to as learning rate and discount factor. Q learning is perhaps the most popular and widely recognized RL algorithm, which we will use in our example discussed below. Q here refers to quality. It is a form of off-policy TD control, meaning it learns the optimal policy independently of the agent's current behavior. Instead of estimating the value of states, Q learning estimates the value of state action pairs, denoted as QSA. The goal is to approximate the optimal action value function QSA, which represents the maximum expected future reward achievable by taking action A in state S, and then following the optimal policy thereafter. The update of QSA is given by this formula. QST at T plus alpha times or T plus 1 plus gamma times the maximum of QSA at the next state, QST at T. Where alpha is the learning rate, for example 0.1 gamma is the discount factor, for example 0.9 R is the reward based on system outcome. Q learning is favored for its simplicity and effectiveness. Its update rule is straightforward, easy to implement, and converges under the right conditions, making it ideal for a wide range of RL problems. We will use it in our simple game example below. In this tutorial, we'll use the game of tic-tac-toe to illustrate the core mechanisms of reinforcement learning. Although it's a simple game, tic-tac-toe offers a clear and accessible way to demonstrate how an agent can learn to make better decisions through trial and error, guided by rewards. By walking through this example, we'll explore how states, actions, and Q values come together to form an intelligent learning process. Tic-tac-toe is a puzzle game for two players, called X and O, who take turns marking the spaces in a 3x3 grid. The first to get 3 of her marks in a row, either horizontally, vertically, or diagonally wins. If all 9 squares or cells are filled and no one wins, it's a draw. Each square on the board can be empty, marked with an X, or marked with an O. To implement a C++ program that trains an AI agent to play the game, we treat each possible configuration of the 3x3 board as a unique state of the system. We represent a state as an integer by assigning a value of 0 to an empty cell, 1 to an X, and 2 to an O. Since there are 9 cells and each can take on 3 values, the total number of possible states is 3 to the power 9, equal to 19,683.
we can label the cells or squares from 0 to 8 as shown here. 0, 1, 2, 3, 4, 5, 6, 7, 8. And we represent a state by an integer. We use 0 to represent an empty cell, and 1 to represent a cell that's marked with X, and a cell that's marked of O is represented by 2. Okay, so like this example, the integer value would be given by this base free number. Say digit 0, because here is empty, so it's value 0. Okay, digit 1, okay, corresponding to the position 1, it is marked by X. Okay, so its value is 1. Okay, and then digit 2, okay, it is empty, so it is 0. Okay, and then digit 3, the square is marked by O, its value is 2. Okay, so its value is 2 here, and then square 4, okay, it is O, so the value is 2, and then square 5 is X, so it is 1. Okay, 6 is 1, 7 empty, so it is 0, 8, it is 0. Okay, so the value of this base free number, okay, can be calculated like this. It is 0 times 3 to the power 0 plus 1 times 3 to the power 1 plus 0 times 3 to the power 2, and then 2 times 3 to the power 3, and so on. Okay, and if you evaluate, its value is 1191. Okay, and the value of a configuration of a board can easily be calculated or implemented, okay, using a piece of code like this. Okay, get state. Okay, the board is an array containing the configuration. Okay, so we start with S to be 0, and multiply M to be 1, and we go through all the nice square and increment S by the M times the value at a square. Okay, so when at the beginning M equals 1, that's 3 to the power 0 times this value I equals 0. Okay, and then the next, okay, is this digit times the multiplier, which is multiplied by 3 now, so it becomes 3. And then next, okay, the multiplier becomes 3 times 3, okay, and the digit is 0 here. And the next will be 3 times 3 times 3, and so on. Okay, so this code will give us the value of the state of the board. Now, in the context of tic-tac-toe, okay, the agent is the AI player, the environment is the game board, okay, and the state is the current board configuration as we just discussed. And the action is placing an X or O in an empty shell, okay, or marking an empty shell with X or O. Okay, so that's the action. And the reward would be +1 for win, okay, -1 for loss, and 0 for draw, okay, or some intermediate moves. And to implement this game, we can store Q values in a 2D array like this. We divide the total number of states to be 19683, okay, that we calculated here, okay, 3 to the power 9. And divide an array two-dimensional, okay, Q, okay, to be the n states, okay, and 9 corresponding to the line squares here, okay, it represents the action, okay, whether we want to put an x at this square or not, okay. So basically the Q corresponds to state and action. Okay. So the crucial part of the program would be to update the Q value or the Q table values. Okay. And we update it according to this Q learning formula, okay, that we discussed here before. Okay. So this routine shows how we do the update. We pass in the parameters, the state, okay, the current state, okay, there's ST here, and the current action, there's AT, okay, and the reward RT plus 1, okay, plus, and also the next state, ST plus 1, okay, next state. Okay. So we first need to calculate the maximum of this QST plus 1 A dash. Okay. So we want to find the maximum Q values for the next state. And it can be easily done by this. We set max Q next this variable to be 0 to start with, and then declare a variable Q, and we go through all the states, okay, and if Q is larger than max Q next, okay, then we set max Q next to be Q, okay. So we find this maximum Q, okay, here, so, and we'll multiply this by gamma, okay. So we update Q state, okay, by this formula, okay. So Q state action is incremented by alpha, okay, times reward, this R, okay, plus gamma, okay, times maximum Q next, okay, this term, okay, minus the QSTAT, that's Q state action here, okay. So a strict implementation of this formula. And to implement the exploration and exploitation, okay, we can write a function like this called choose action. Okay, basically we choose the best location, that means action, to mark X or O. Okay, so we pass in the state S, okay, and a Boolean variable explore to tell whether we want to explore or exploit. Okay. And if this is true, then we calculate a random number, okay, between 0 and 1. If this is more than a specified value, small value, maybe less 0.1, we call it epsilon here, okay. And of course, explore equals true, okay. Then we do the exploration. So exploration means to explore the board with empty spaces, okay. And we just try randomly to pick randomly, okay, any of the random space, okay, and return that to the calling routine. So if we here the moves, okay, n plus plus is I, okay. This will tell us where we want to mark, okay, the symbol. So totally there are n empty spaces, okay, and we picked a random one, okay, and return that. Now, if this is not true, then we do the exploitation. Exploitation means to choose the action with maximum quality. So we first set the best move to be -1 and declare a variable max q to be a large negative number. Okay, and again we go through the board. Okay, whenever we find an empty square, okay, we set the q, this q, to be QSI from the Q value table. Okay, and if Q is larger than this max Q, we set max Q to be Q, okay, and set the best move to be I. So that means we will find the location that with the maximum Q value. Okay, and we pick this location, okay, to mark, okay, the symbol. So there's the implementation of exploration and exploitation. This is the complete program of a C++ implementation of the tic-tac-toe game using reinforcement learning with Q-learning. So we first define the constants alpha to be 0.1, gamma to be 0.9, epsilon to be 0.1, the constants we mentioned earlier, and the total number of states is 1683. And we define an enum player to have elements empty x, o, and we assign 0 to empty. Automatically the value of x will be 1 and the value of o will be 2. Okay, so we declare board to be an array of 9 players, and Q is the Q table, okay, a 2-dimensional array, okay, with n states, and 9 basically this specifies the state action. Okay? And we mentioned that a state is a configuration of board 2 to 3 to the power 9 different states or this number. Okay? And an action represents the location at the board where one marks X or O. And the function we set board is to make all 9 locations of the board to be empty. Pinboard is to print out the 9 squares of the board, okay, with the marked symbol. In initialization is first we set the board and set all the values of the Q table to be 0. Okay. Get state, we mentioned this before, it returns the state of the board, okay, which is specified by an integer. And update Q table, we also discussed that above. Okay. It basically implements this equation. Okay, update Q table. And also we discussed choose action. Okay. Now this function is winning, is to return whether the player that we pass in is winning. Okay, so this can be done by checking the position horizontally, like 0, 1, 2, 0, 1, 2. Okay, if all this belong to the same player, then it wins. So we return 2. Or say it vertically. Okay, like 0, 3, 6, 0, 3, 6. 147, 147, 258, 258, or diagonally 048, okay, 048, or 2, 4, 6. Okay, if they all belong to the same pair, okay, 0, 1, 2, okay, then the player is winning. Okay, we check all these 8 different cases. Okay, that's why we have this I. Okay, we store this in this two array. Okay, I will go for each of these the free values. If this is not true, then we return false. And if there's no empty space, okay, then it is a jaw. Okay, otherwise it's false. Okay. And so this is the training routine that trains the AI agent with that many episodes, that many times. Okay, a parameter we pass in. And we define the variables win, draw, state, action, next state, and we also declare a struct called state actions. Okay, it is for recording states and actions of players X and O as they play. When we mark this square, okay, then the state and action, okay, could be recorded using this structure. Okay. So the state is an array of 9 integers. Action is an array of 9 integers reflecting the board. Okay, and we start with n equals 0. That tells us how many times we have recorded that state actions. So once we got put an O here, then the n will be incremented. Okay, so it is recorded by this function put as a. Okay, and then next time we put it here, then again this function put will be called. Okay. So we first do the initialization, and in this for loop, first we reset the board, and we start with current player to be x, and declare these 2 variables x as a, o as a, for recording the state actions for X and O respectively. Okay. So in this loop, while true, okay, we do this. Okay, so we break out of this loop when there's a win or a draw. Okay, and in this loop, we switch the pair at the end of the loop. If current pair equals X, okay, next time it go back to here, it becomes O, okay, and then the next time it becomes X. Okay. Now, in this loop to begin, okay, we get the state of the current pair, okay, the current state of the current pair, and then this function choose action will tell us what action we want to do. That means where to mark the current pair. Okay, so we choose whether we do the exploration as well as exploitation. So this is true. Okay. And if action is more than 0, then we break out of the loop. Okay. And if the current pair wins, okay, or draw, okay, then we also break out of the loop. Okay. But if it is not even a draw, we continue. Okay. And we also record, okay, the state actions using the variables x as a and o as a. So if the current pair is x, okay, then we put the state, okay, the state from here, and also action. So where we put the mark the square. Okay, so we record it in x as a. Okay. If the current pair is O, we record that in O as a. Each time we record it, increment n. Okay, so we continue to mark the empty space, okay, alternatively, okay, O and then X, okay, until it is a win or a draw. Okay, then we break out. Okay. But before we break out, we will calculate the reward. Okay. So the Rx here is the reward for pair X. Okay, if pair X wins, okay, the current pair is X. Okay, then the reward of it is 1. Okay. Otherwise, if the current pair is not X is O, this means O wins, then the reward will be -1. For the other case is 0. Okay. And the reward of O, our O is always the negative of our X. If our X is 1, then our O is -1. If our X is -1, our O is 1. If our X is 0, our O is also 0. Okay. Then we use what we have recorded. We update the Q table, okay, with all the state actions we have recorded. Okay, as we put O here, X here, and so on. Okay, because the number of times we have marked, okay, the current pair is given by this n, like this. Okay, XSA is the number of times you mark the X in the remaining spaces. So we update the table. XSA state I, XSA action I, and then we put this Rx to revert. And also the next state is calculated. Do the same thing for the OSA. Okay. Then we do this for many times. Okay. Then we have a good Q table, okay, for us to use. Okay. This function play is to let human play against the trained AI. So first we set the board and set the current pair to be X. So that means the AI is X, the human is O. Okay. So if the current pair is O, then that means humans move. So we have to mark 0 to 8. Choose a number between 0 to 8. Okay. If a move is more than 0, move is larger than 8, and the board is not empty, then the move is not valid. So we have to try again, continue. Okay. Otherwise, you mark the board with the move that we enter to be O. Okay. The human is O. Okay. And this part is for the AI agent. Okay. So we obtain a state from this function, get state, and also the AI move is given by this function, choose action with state and false. We don't need any more exploration. So this is set to false. Okay. So we have a Q table for us to use now. Okay. And then we mark the board with this move with X. Okay. And then we print the board to show the readers, that the users. And if it is winning, okay, if the current pair is X, okay, that means AI wins. Okay. Otherwise, then the human wins. Okay. Otherwise, if it is a draw, then it is printed out, it is a draw. Okay. If it is not a win, a draw, that means we need to continue to play. So the current pair, okay, will be switched. If it is X, then it becomes O, and if it is O, it becomes X. This is the main function. To start with, use this SRAM to set a seed for the random number generator that we use in the exploration. Okay, and then train the agent for 50,000 times, and then we play. Okay. Let's copy this program into a file and compile it. So copy it. And we paste it into this file. Okay. save it. So this is the program we just discussed. Now let's compile it. So exit here. So we compile G++, tic-tac-toe.cpp -o, tic-tac-toe. Okay. So it compiles. Okay. And now let's execute this. Okay. So the AI has moved to 2. Okay. And as our move, so let's try maybe 4. Okay, so AI put this. Okay, so let's try 1. Okay, so AI moves at 7. Okay, and so let's move at say 8. And so let's move at 6. Okay. So it is a jaw. Okay, the board is filled. Now let's try again, execute again. Okay, so the AI moves at 4. Okay, so now let's try it, maybe 3. Okay, and so AI moves here. So let's try 2 to block it. Okay. And now we are in trouble. Okay, so we can block either one. So let's try it, 1. Okay, so AI wins. Okay, and let's try one more. And so do this. Okay, let's try 0. Okay, so it does this. Now, suppose I do something interesting. Okay, suppose I do this here. Okay, there is 6. Now, so it blocks me. So, but you can see that even though it can win immediately, but it doesn't matter because it will always win. It has 2 choices. Okay, now let's see. We block it here. Okay, 0, 1, 2, 3. It should be 4. Okay, so AI wins. Okay, so sometimes the agent looks at the long-term effect, okay, instead of the immediate reward. Okay. Maybe we can try one more time. Okay, so again, so we try 0. Okay, so 7. Okay, and this would be 0, 1, 2, 3, 4, 5. 5. It should be 5. Okay, and then now we have to block it. Okay, 6. Okay, so it is a jaw. Okay, so that means the AI is intelligent enough to win the game when there's a chance. Otherwise, it would pay to a jaw. Okay. So that's what we want to present today. So if you feel that this video is helpful to you, please give it a like. We will see you next time. Thank you for watching. Bye-bye.